Today we will solve this problem from Romanian Mathematical Magazine. This problem was proposed by Ankush Kumar Parcha from India, and let's see how do we solve this problem. The first thing that we can do in solving this problem is to write this in terms of a sum. So basically, this can be written as sum going from k equals to 1 to infinity, and then there's 1 by k in the beginning of integral, and the integral goes from 0 to infinity, and then we have tan inverse of k square x square by 1 plus k square x square dx. Yeah, so this is basically our problem in summation notation. Yeah, and we just need to find this. So the first thing that we can do is uh, we can basically we can basically just let y equals to kx. Yeah, if you let y equals to kx, you will get tan inverse y square, yeah, by 1 plus y square, and since y equals to kx, our dy by k equals to dx. So this will be dy by k. Now 1 by k can be taken out, yeah, from the integral, and that's why we will have k from 1 to infinity 1 by k square. And now to solve this integral, we can basically break this integral from 0 to 1 and 1 to infinity, yeah, and then we can take reciprocal on the 1 to infinity side, because and that will help us, because tan inverse y square plus tan inverse 1 by y square is just pi by 2. So let's try to do that. So integral from 0 to 1 tan inverse y square by 1 plus y square dy plus integral from 1 to infinity tan inverse y square by 1 plus y square dy. Now the next thing that we would like to do is, over here in the second one, we will change y to 1 by y. Yeah, and then we get sum from k equals to 1 to infinity 1 by k square. Yeah, and this is from 0 to 1 of tan inverse y square by 1 plus y square dy. And over here this goes from 1 to 0. Yeah, and now this will be tan inverse of 1 by y square by, now if there's 1 by y square, we will have y square plus 1 and then y square over here as well, and then dy will be minus 1 by y square dy. Yeah, now y square cancels out, and we can use the negative sign to reflect the integral, yeah, to reflect the limits of integral. So we will have sum from k equals to 1 to infinity of 1 by k square, and then integral goes from 0 to 1 of tan inverse y square by 1 plus y square, and then dy plus integral goes from 0 to 1 of, now tan inverse 1 by y square can be written as cot inverse y square. Yeah, cot inverse y square by 1 plus y square dy. Now since both the integrals have the same limits of integration, so we can combine them into a single integral, and that gives us sum from k equals to 1 to infinity 1 by k square of integral from 0 to 1 tan inverse y square plus cot inverse y square by 1 plus y square. Now this is in a purely simple form. Yeah, because we know tan inverse theta plus cot inverse theta is actually pi by 2. And if you want proof of that, it's pretty simple. So let's say we have this triangle AB, yeah, 90 degree. Now let's say this is alpha, this is beta. Now let us try to think that, like, let's say x is a by b, yeah, and then our tan inverse x will be alpha, yeah, and then cot inverse x will be uh, tan inverse. Okay, so basically tan of alpha is a by b. Okay, and now cot of beta cot of beta is a by b. So now cot inverse x is beta. So now if we add both of them, you will just get alpha plus beta, which is 90 degrees. Yeah, that's why this is pi by 2. And we have sum going from k equals to 1 to infinity 1 by k square. This is pi by 2 is a constant, can be taken out, integral from 0 to 1 by 1 plus y square dy. Now this is a pretty simple integral, which is just tan inverse y. Yeah, so I'm going from k equals to 1 to infinity 1 by k square times pi by 2, and this is tan inverse y from 0 to 1, so that's pi by 4 minus 0. Okay, now pi square by 8 can be taken out, and this sum is just Riemann zeta of 2, so that's just pi square by 6, and that gives us the answer, which is pi to the power 4 by 48, and that's the answer. Let's check the answer if it's correct or not. Okay, that's the correct answer, and this was a kind of simple integral, just that we had to break it into two integrals and then use the reverse property, and then the sum of the inverse trigonometric functions, and we solved it in zeta of 2. So that was it. Hope you enjoyed the problem, and look forward to seeing you in the upcoming videos too. And thanks to Ankush Kumar Parcha for the problem.